Assessing probability of failure, POF, analyzing risks to predict potential system failures. Overview of probability of failure in RBI, Introduction to probability of failure, POF, units of measure in POF analysis, qualitative POF ranking, types of POF analysis, qualitative POF analysis, quantitative POF analysis, key determinants of POF, POF evaluation steps, inspection effectiveness, limitations of inspections, keys to success in assessing POF. Probability of failure, POF, is a core element of risk-based inspection, RBI, frameworks used in the process, energy, and manufacturing industries to manage asset integrity. POF represents the likelihood that a piece of equipment will experience a loss of containment or functional failure within a defined period. In RBI, risk is typically expressed as the combination of probability of failure and consequence of failure, making POF a critical driver for inspection planning, maintenance prioritization, and lifecycle decision-making. A well-structured POF assessment enables organizations to move away from time-based inspection strategies and toward risk-informed decisions that optimize safety, reliability, and cost. This overview slide introduces POF as a relative measure rather than an absolute prediction, emphasizing its role in comparing equipment, systems, or damage scenarios. It also highlights that POF is not limited to corrosion or material degradation alone but is influenced by operating conditions, design margins, inspection effectiveness, and historical performance. By understanding POF at a high level, stakeholders can better appreciate why consistent methodologies, clear assumptions, and documentation are essential to producing credible and repeatable RBI outcomes. The introduction to probability of failure focuses on defining what POF represents and how it is applied within an RBI program. POF estimates the relative likelihood that an adverse event, such as a leak or rupture, will occur due to one or more damage mechanisms acting on equipment. This assessment must consider all credible damage mechanisms to which the equipment is susceptible, including situations where multiple mechanisms interact, such as corrosion combined with creep or fatigue. In addition to damage mechanisms, other contributors to loss of containment may exist, including operational errors, design deficiencies, external events, or environmental extremes. While these contributors are not always explicitly modeled, they can influence overall failure likelihood. The objective of introducing POF is to establish a structured, repeatable, and technically defensible approach that supports decision-making. This slide sets the foundation for understanding why engineering judgment, supported by data and standards, plays a central role in POF estimation and why transparency in assumptions is critical for consistency across RBI assessments. POF is typically expressed as a frequency, representing the expected number of failure events over a defined time interval or operational occasion. Commonly, this interval is 1 year, resulting in units such as failures per year, but it may also be expressed per run length or campaign, depending on the operating context. Understanding units of measure is essential because they directly affect how POF values are interpreted and compared. In qualitative analyses, POF may be categorized using descriptive rankings such as low, medium, or high. However, even in these cases, it is considered best practice to associate each category with an approximate numerical frequency range. Doing so improves consistency, reduces ambiguity, and helps align qualitative judgments with quantitative risk tolerances. This slide emphasizes the importance of clearly defining the units of measure used in a POF analysis to ensure that results are meaningful, comparable, and usable for inspection planning and risk management decisions. Qualitative POF ranking systems are commonly used when detailed failure data are limited or when a high-level screening assessment is required. These systems classify equipment into discrete categories such as low, moderate, or high probability of failure, based on engineering judgment, operating history, and inspection results. Although qualitative in nature, these rankings are most effective when supported by approximate numerical frequency ranges that define the boundaries between categories. This approach provides clearer guidance to inspectors and engineers and helps ensure that different assessors reach similar conclusions when evaluating similar equipment. The slide explains how qualitative rankings support prioritization while acknowledging their limitations, particularly in terms of precision. By linking qualitative categories to frequency ranges, organizations can improve the robustness and repeatability of their RBI programs while maintaining practicality. POF analysis methods exist along a continuum ranging from purely qualitative to fully quantitative approaches. Qualitative methods rely primarily on engineering judgment and categorized rankings, while quantitative methods use numerical data, statistical models, and probability distributions. In practice, most RBI assessments employ a hybrid approach that blends qualitative insights with quantitative inputs. This slide explains that the chosen method should be appropriate for the quality of available data, the criticality of the equipment, and the objectives of the analysis. It also highlights the importance of structuring the methodology so that sensitivity analyses can be performed, allowing assessors to understand how changes in input variables affect the resulting POF. Documenting the chosen approach and assumptions is emphasized as a key requirement for credibility and auditability. Qualitative POF analysis involves identifying equipment, materials of construction, and process conditions, then evaluating susceptibility to damage mechanisms based on experience and historical knowledge. Engineering judgment plays a central role, supported by inspection findings, maintenance history, and an understanding of future operating plans. Equipment is typically assigned to a probability category that reflects its relative likelihood of failure. This slide explains how qualitative analysis is particularly useful during early RBI implementation, for screening large populations of equipment, or when data availability is limited. While less precise than quantitative methods, qualitative analysis can still provide significant value when applied consistently and by qualified personnel. The importance of standardized criteria and clear definitions is emphasized to minimize subjectivity. Quantitative POF analysis uses numerical failure data, probabilistic models, and statistical distributions to estimate the likelihood of failure. This approach may utilize equipment-specific failure histories or broader industry, company, or manufacturer databases when specific data are unavailable. General data are often adjusted to reflect equipment-specific conditions such as material, environment, damage mechanisms, and inspection effectiveness. This slide explains that quantitative analysis can provide more detailed insights, including time-dependent failure probabilities and uncertainty ranges. However, it also requires higher quality data, greater technical expertise, and careful validation of assumptions. When applied appropriately, quantitative POF supports more precise inspection optimization and long-term integrity planning. Two primary factors determine probability of failure: the active damage mechanisms affecting the equipment and the effectiveness of inspections in detecting and monitoring those mechanisms. Damage mechanisms and degradation rates are driven by operating environment, materials of construction, and loading conditions. Inspection effectiveness determines how well deterioration is identified before failure occurs. This slide highlights that POF is not solely a function of how fast damage accumulates, but also of how effectively that damage is managed through inspection, monitoring, and maintenance. Understanding the interaction between these determinants is essential for realistic POF estimation and for identifying opportunities to reduce risk through improved inspection strategies. Determining POF involves a structured sequence of steps that ensure all relevant factors are considered. These steps include identifying credible damage mechanisms, determining susceptibility and deterioration rates, evaluating past and future inspection effectiveness, and estimating the likelihood that damage will exceed allowable limits and result in failure. This slide explains that the evaluation should consider both current and future operating conditions and may involve assessing multiple inspection strategies, including scenarios with no inspection. The outcome is a defensible estimate of POF for each damage mode and time period, supporting informed RBI decisions. Inspection effectiveness is a measure of how well inspection activities reduce uncertainty about the condition of equipment. It depends on the suitability of non-destructive examination methods, coverage, frequency, and the competence of inspection personnel. Different damage mechanisms require different inspection techniques, and an inspection effective for one mechanism may be ineffective for another. This slide emphasizes that accurate POF estimation requires evaluating inspection effectiveness separately for each credible damage mechanism. Improving inspection effectiveness through better methods, coverage, or frequency can significantly reduce POF without changing operating conditions. Despite their importance, inspections have inherent limitations that can affect POF assessments. These include incomplete coverage, technical limitations of inspection methods, inappropriate technique selection, human error, and procedural non-compliance. Changes in operating or environmental conditions can also invalidate assumptions based on previous inspections. This slide discusses how recognizing and accounting for these limitations is essential to avoid underestimating failure probability. A realistic POF assessment acknowledges uncertainty and incorporates conservative assumptions where inspection effectiveness is limited. Successful assessment of probability of failure requires a disciplined and comprehensive approach. Key success factors include addressing all credible damage mechanisms, understanding interactions between mechanisms, defining clear units of measure, and selecting appropriate methodologies. Using equipment-specific data, accurately evaluating inspection effectiveness, and correctly estimating deterioration rates are critical to producing realistic results. This concluding slide reinforces that POF assessment is not a one-time activity but an ongoing process that evolves with new data, inspections, and operating experience. When applied correctly, POF assessment becomes a powerful tool for proactive integrity management and risk reduction.